very important that we do something here that will transcend time and generations of kids growing up and all those sorts of things, but do so in a way that's completely different from our homes in Melbourne. I'm John Wardle, founding partner of Wardle, and we're here in Burnt Earth, our family's new fish house. A lot of ASAP actually really stems from a knowledge of geology. This ASAP has right at the very end of a vast landscape that's called in the 1920s that has this vast, beautiful ochre-coloured cliff face, which was really the genesis of the idea of both the material and the tonality of these clay bricks in their rusticated form. Clay actually a torn surface. It's not broken, but it's torn. It means the surface is wonderfully uneven and every brick literally is different. And the coloration is exactly as we could match to the cliffs at Point Roadnote. The house starts off at the front, facing the ocean, and the courtyard is an informal living zone. The idea of the kitchen really is one of a place that assumes that there are many cooks. So the vast, big, square, central terracotta iron bench sits there really as evidence of that idea. The space then bends around into a dining area with a reading nook, a window seat that looks back into a courtyard, another window that then looks out toward where water at times will fall, and then get up the stairs. At that point you're aware of this vast linear space, this study that appears to float, this wrapped, hand knotted screen made in Vietnam. And at the top of the stairs then you'll see soon a small living space that is reduced from the footprint of this area below, particularly to gain the ingress of light by putting this wood and pulling the floor plate back. At times like this, the winter light can then burn right at the very heart of the house. Very often we employ materials or systems that came out of initial moments when you're setting something and wondering how it was made or who made it. And through our relationship with Art and Donuts, an introduction to Cotomonetti, a relationship was formed that has transcended many projects now. So very early on when considering the nature of the materiality of this house, to wish to draw upon this beautiful material made on the other side of the world and bring it to this place in Western Victoria.
Collected the Arapato, the crudo extruded terracotta tiles from Cotomonetti for the kitchen and along the floors and then up onto the bench top. These are really beautiful, unique tiles produced by Cotomonetti in Italy. Their manufacturing techniques have endured over 8 generations of makers and they work with extremely skilled artisans. These terracotta tiles are actually really great for kitchen bench applications. They have characteristics of being robust, they have high resistance, and they have that beautiful colour which is produced from the natural clay which is sourced in the Tuscany region. For his bathrooms, John has chosen the Agape Petra Basin, which is made out of a really interesting material called cemento skin. This is a colour-enriched concrete and it's very natural in its finish. And the way it's been designed is quite beautiful. Its form emulates that of a stone, which encourages the water to run over the form of the basin, almost as if it was running over a stone.
theory, GPU databases can run certain analytical queries faster. Queries with large sorting, large aggregations, large joins, maybe. They can do faster some complex calculations like conversion between different coordinate systems for geospatial processing. But in practice, they have to specialize the code for certain operations, and only a small subset of operations is actually accelerated. They don't scale well past the size of GPU RAM, like 16 gigabytes, maybe 80 gigabytes if you pay a ton of money for your GPU. And the code is quite difficult to maintain. And the result is, it looks as follows. So here is two examples of GPU databases that are still alive. Heavy AI and Kinetica. And you can see a lot of, here is a benchmark, open source Geekbench, and you can see a lot of black entries with these school and bones. And these are not the cases when they are slower. These are the cases when they cannot process some queries at all. So they either crash, they either show some exception and refuse to process the query, but they are basically non-functional for this pretty basic benchmark. And Geekbench is really quite basic. But in theory, they could provide some benefits in very narrow cases when the amount of computations is significantly large compared to the amount of processed data. Okay. Maybe they are actually good at providing some visualizations. Like here is a picture from the website of Heavy AI, named AI and Natural Language. Here on any website of modern database there is AI today. To query 1 billion flight records. So I thought maybe I can just make something as impressive using my favorite database. And my favorite database is ClickHouse. So I implemented a website allowing you to explore not 1 billion records, but 100 billion records in real time in the browser. Let me open this thing. I hope it works. Yes, it works. And it is interactive. And what it does, it is a single page application in the browser. It has a SQL query, parameterized query to ClickHouse. It is sent to ClickHouse for every tile. The result set is returned and visualized in these pictures. And what is on the picture? Do you recognize what it is? Let me zoom in. Amsterdam Schiphol Airport. I can even take a look and change to another query that filters by different airlines. And I can zoom in even closer and see, for example, where are all KLM airlines are located. Or I can look at helicopters and see where helicopters fly. And you can see, for example, here is VUMC. Yeah, so it works. Okay, let me go back to my presentation. I hope this use case is hosted. Okay, what about another use case? Web API databases. Do you recognize this database? This database, what is it? Exactly. I thought someone would say DuckDB, but it has quite a strange logo. It looks like a lot of birds that have no idea where to fly. So let me read the description. SQL at the edge provides data for your dashboards and visualization just by executing SQL straight from user's browser. But isn't it exactly input-output formats for presentation, for processing, query caching, etc. But the question is, why should not it be the part of the database itself, the database server? A good database, if it is not DuckDB, is already a server. It already provides authentication, access control, rate, supposedly rate limiting, caching. So there should be nothing wrong making a database server also a web server. And my web database does it. It provides HTTP, HTTPS API out of the box. So you can query from the browser, from JavaScript, using this fetch function with query as simple as this. Okay, another use case. Time series database. There is a huge number of time series databases. Influx, with timescale, CDS, even.
Hey everyone, I'm Brian Cancel. It's great to be back at Motoberfest. Stephen, you often say that this is an opportunity for us to have those conversations, get those presentations that we never see or hear anywhere else. They're very
There's a 9-week release, because every 9 weeks there's a new release going on, right?
So there's Linux as a release, just when it's on. And then merge Windows considered open. And then for 2 weeks, all the maintainers send Linux all the stuff they had pending in the last release. We have 2 weeks add all new features. And then he does release candidate 1. From there on, it's bug fixes only for the next 7 weeks. So it's bug fixes only, bug fixes only, bug fixes. It's regression fixes, we'll revert things, no new features.
Do I understand correctly that in the case of Linux, is this a thing where every 9 weeks there will be a release?
It's time-based. So we have that 2-week window of merging all the new features to Linux that have been in our tree and accepted already and proven to work. And the window is short, 9 weeks. We used to have 3-year-long development cycles. And the problem there is, even if you have 6-month development cycles, there's that fear of, you have a feature. I want to take your feature, but it's not quite ready. Do I want to wait? And things like that. But if you know that you can get your feature in 9 weeks from now, and it's just not ready, it's not ready. The pressure is off me as a maintainer to take your new feature until it's ready.
Linux is the world's most widely used operating system thanks to powering most Android devices, servers, smart TVs, and embedded systems. But how is it actually built? Today we sit down with Bretko Hartman, a Linux kernel maintainer for 25 years, who is one of the 3 Linux Foundation kernel fellows. In today's conversation we cover details on how widespread Linux is, and why mobile versions of Linux have 3 times the lines of code as the server versions. What exactly it takes to get a change accepted in the Linux kernel and merged by Linus Torvalds himself. How the Linux kernel operates with 4,000 contributors from 500 companies per year with just email, Git, and web project managers, and many more details. If you're a software engineer, you will use Linux directly or indirectly, and this episode will help you understand why it's so widespread and how it's a lot easier to contribute than most people would assume. If you enjoy the show, please subscribe to the podcast on any podcast platform and on YouTube. Thank you.
Welcome to the podcast.
Thanks for having me.
I think as software engineers, we know Linux is important in the sense that it's running on most web servers that we use and run. It's a desktop OS that some people use, and it's of course, you know, powering, a fork of it is powering Android, but what is there to know about Linux? How big is this thing? How complex is this thing?
Well, it's it's an operating system, so it's kernel. We took over the world without anybody noticing. Joke, it's Android devices are 4 billion Android Linux users out there, and they don't realize it. That's everything else is a rounding error, which doesn't make the server people happy with me. But it's true, it's in everything. It's in all the embedded devices, it's in the air conditioning units, car electric charging ports, satellites, runs the International Space Station.
Really?
Yeah. Air traffic control for Europe and probably the US, all the financial markets. I don't think it's in the cameras that we're using. It's, I don't know of any place that hasn't taken over. Remember the top 5 selling laptops for the past 15 years, Chromebooks, they're all in this space. Not Apple, but Chromebooks are. iPhones. So every 5G modem out there is running a copy of those.
Really?
Yeah.
Wow.
So now with Apple doing the new chip, I don't know if it's a new one, but Qualcomm, all the 5G modems, probably the 4G, I'm not sure, but I know all the 5G modems have Linux inside.
This episode was brought to you by WorkOS. If you're building a SaaS app, at some point your customers will start asking for enterprise features like SAML authentication, skin provisioning, and fine-grained authorization. That's where WorkOS comes in, making it fast and painless to add enterprise features to your app. Their APIs are easy to understand, and you can ship quickly and get back to building other features. WorkOS also provides a free user management solution called AuthKit for up to 1 million monthly active users. It's a drop-in replacement for Auth0 and comes standard with useful features like domain verification, role-based access control, bot protection, and MFA. It's powered by Radix components, which means zero compromises in design. You get limitless customizations as well as modular templates designed for quick integrations. Today, hundreds of fast-growing startups are powered by WorkOS, including ones you probably know, like Cursor, Vercel, and Perplexity. Check it out at workos.com to learn more. That is workos.com.
Well, first of all, I'm just reflecting on why I never kind of, thought about it like this, because in my mind, it was always like, it's Debian, Red Hat, it's on a server side. And maybe that's because that's where I actually see where, of course, there's right now I'm a Mac user, and there's the Unix influence, which is an influence, it gets pretty close. But I think it's good to reflect on how many things it actually runs. In terms of the kernel itself, like how large is it? And I know, for different devices, it'll be spread differently. For server-side Linux, for an Android device, it'll use different parts of the kernel. How big is this in terms of contributors, lines of code? I know lines of code is not a great measure, but it is a measure.
That is interesting. So we have just under 40 million lines of code. That's a lot. That's all the kernel. That's the kernel is 4 parts, like 5% of that everybody runs, and then the rest of it is hardware support, different drivers, different devices, different architectures, different chips. So your laptop runs about 2.5 million lines of code. Your server runs about 1.5 million. Server. Those are very simple machines. Your phone runs about 4 million. Your phone SoCs are the most complex pieces of CPU and interaction out there. They're just crazy.
And why is okay, can we just pause for a second?
Yeah.
So again, lines of code we know is not a perfect measure of complexity, but in this sense, comparing it between the two of them with the same code base is somewhat. So you said roughly, give or take, the server is 1.5 million, a phone is 4 million, like 3 times the lines of code for a phone. Why the difference? Even though I would think that the server, does all this mission critical stuff.
A server is really simple. CPU and a network card and storage. That's it. So SoC on a phone you have power control, you have clocks, you have 5 different buses on there talking to different types of devices. You have battery control, you have talking to your modem. You have another version of Linux in the modem. You got USB out the back. You got USB bypass to talk to the audio side. You have audio drivers. You have a zillion different clocks and PHYs and all sorts of stuff in there. And it's an 8-core machine. There's 8 processors in that thing. Those are not trivial things. And sometimes those processors are different sizes. So you have big and little sizes, which add the complexity just for some control, for some power management. But they all run the same core of Linux, but it's the drivers and the devices and things like that. So your Pixel phone, the Pixel phone, Google ships a core kernel that all Android devices have, not hardware specific, it's an ARM64. Pixel has 300 other drivers they add to get the Pixel phone working. Some of these are tiny, this is this tiny chip, this is this tiny chip, but your phone is really one of the most complex beasts out there for software.
So, is it safe to say that, you know, the complexity and, you know, the lines of Google to some extent scale, that has to do with the hardware, the capabilities, and you know, not about, you know, like how mission critical, because of course the phone OS needs to be stable, the server needs to be stable, my TV needs to be stable, so you know, that's just kind of given, right?
Yeah, and all TVs for the past 15 years are all running Linux. So that's
So my Samsung TV is running
Oh,
Linux.
yeah. My Samsung washer and dryer running. So, your Samsung watch is running Linux. Yes, so, Samsung has run, distro. Oh, it's really nice. It's all due down to the complexity of the hardware. So the kernel controls the hardware. The job of Linux is to make all the hardware look agnostic to programs. So you can write the same user space program and run it on the same, different hardware, and it just works. Kernel's job is to manage memory and devices in a common way and provide that to user space. It's not we joke in the kernel, like user space is just a test node, but I mean, it's a tool there for you to actually solve your problems. So when you're running servers, you're running to put messages through and network and store and stuff. That's your load. That's what they're there. For a phone, you want to control the display, you want to talk about the modem, you want to talk on the thing, you want to listen to audio. Etc.
And I'm just want to touch back on the kernel, because like I'm not a Linux developer. Like I know, you know, I've heard of the kernel. In my assumption, it is the critical parts, as you said, the thing that runs immediately, and then it will, you know, the user space will run on top of it. But what is the differentiator? What makes a kernel? And you said it's about 5% of all of these things. How do you split this? Or like, is there a definition of? Again, you're a kernel developer, so I'm trying to get a sense. How can, like, someone who let's say I'd like to contribute to Linux and I understand how it is. Eventually, I'm going to figure out what this kernel is. But what is it? What makes kernel and non-kernel?
So kernel versus user space. So there's an idea. Chips have a protected mode and a not protected mode.
Yeah.
In a very simplified way. There's different levels of protection. So the protected mode is where the operating system runs, the kernel.
Yeah.
And that is where we share all the resources, one flat address space.
Got it.
And we're not isolating processes.
Got it.
So a user space process then runs on top of that, and we isolate them. They all individually think they have the whole machine, but they don't.
Yeah.
So it's multitasking. We can run multiple programs at the same time. And the kernel is there to give you memory, to give access to storage, to give access in a common way, to give access to the network in a common way, or provide the pipes to go around the network stack in the user space. Some people don't like using Linux network stack, they have their own. To provide a way for all your different mice to show up in user space in a common way. We know all the different stuff, USB storage devices, your graphics controller. We provide a way to make it so that user space can talk to the kernel in an agnostic way, and their stuff will just work because all the graphics work the same interface. We talk to the keyboard to all the same things. So it's a commonality of providing a shim layer of the hardware.
And then, for example, drivers. Do they always live in the user
So
space?
all our drivers live in the kernel. So the kernel and drivers are all, Linux is not a micro kernel architecture, it's a monolithic. So the code is all in the same address space. So a bug in any one of them has a chance of taking apart the kernel data. So Linux ships all the drivers for all architecture in one big tile. We use less than 40 minutes, that's good.
Yeah.
Other operating systems try and go up there and have split things off. So for Windows is their kernel, and then you can put drivers additional on the top. We tie everything together in one big giant blob. Theirs is still monolithic. Any driver in there can crash the kernel within reason. In that way, we can refactor the way the interfaces between drivers and the kernel are. Linux drivers are on average 1/3 smaller than other operating system drivers because we can see the commonalities. If you send you have 3 different drivers for 3 kind of same hardware, well, let's combine them all, make it smaller, and refactor things and make it easier. And this changes API.
And this has to do with the open source approach, right? That you see it like
so we see all this common code, we can refactor it, we can make it better and cleaner, but we're not tied to any fixed interface. Our fixed interfaces between the user space and the kernel, we will not fix that. That's our guarantee. We've guaranteed it for a long, long time. And so we always want you to be able to upgrade your kernel and not feel worried that your old programs are going to crash. So you should always be able to upgrade. That's our guarantee. If it does break, that's our fault. We'll address it. There are some exceptions. There's some gray areas. There's some really low-level parts between user space and kernel that we kind of work around. And we argue about these all the time. But we never try and break user space on purpose.
Yeah.
A lot of times we do accidentally. We'll fix that. That's our only really rule of kernel development. Don't break user space on purpose.
And so when we're talking about the 1.5 million lines per server, we're talking about a kernel.
Yes.
4 million
drivers.
kernel plus drive. Well, because it is part of the kernel. And then, we have this 4 million line of tarball, and then every platform will kind of take their parts of it. They'll take, what is relevant for their use case capabilities, drivers, other parts. Okay. And then this is why I guess Raspberry Pi, you're gonna say it's gonna run this line on Linux, right?
Of course. That's Raspberry Pi. Yes. Those things are everywhere. That's what's in all the electric charging stations. Those are Raspberry Pis.
Electric, really?
Yeah, where you plug your car into.
Yeah, that's Raspberry Pis.
Yeah.
Wow.
Because it's a really cheap industrial thing. Lots of signage now. Those are all running Raspberry Pis.
Well, I guess it was safe to assume they're not running Windows, to be fair. So.
No, yeah. So the Dutch signage for the trains, those are all running Linux. Sometimes you'll see a crash on this.
Can we look at a specific example of how development actually flows through with a specific patch?
Before I show you a specific example, so I'll say, we have 4,000 developers last year. So they make a change. So those 4,000 developers will send an email to a maintainer. The maintainer maintains a subset of the kernel. Every part of the kernel is owned by somebody.
And then you are one of these maintainers.
So then, I maintain some drivers and things like that, but then those maintainers send things off the tree to a subsystem maintainer. So like USB serial, then will get sent up to USB, and then USB will go to Linux. So it's kind of a pyramid scheme that way. We have we have like 800 maintainers, and we have the middle section. We maybe have about 200 different trees there, and then in our testing environment, all those trees are tested every day. They're all merged together, and things that happen. So we have this kind of hierarchy of developers and maintainers that way. And part of the hierarchy is the human aspect. So if I take code from you as a maintainer, I'm never responsible for it because my name's in it. So if it's a simple one-off or it's a simple driver that nobody cares about, except you, great. I know you're the only one that's going to be affected by it. It's fine.
Yeah.
But if it's the core part of the kernel and I take changes from you, now I'm responsible for it if you disappear. So I have to trust that either you're going to be here or that I understand it good enough that I can maintain it. So part of Linux development trust, or model is trust, and it's trust in human interaction. Like I will take stuff from people, if they whatever they send me, because I trust not that they got it right, but they'll be there to fix it when they get it wrong. Because we all get it. Yeah. And that's the part. So that's the trust that we have, and then we've been burned in the past by some major features where it landed in the networking core subsystem a long time ago, and then once they landed and merged and taken, the email address kind of disappeared. And the network developer said it took 6 months to unwind the mess. So it's hard to change the core part of the kernel for good reason, because it affects everybody, and also good reason in that we want to make sure that you are going to be there to fix it if it breaks.
Yeah.
But for drivers and things like that, we'll take any drive-by. It's really simple.
Yeah.
It's very simple. But that's the hierarchy, so change flows up the tree that way.
Yeah.
So I guess so here is a change. So this was written by someone named Chester. He made a change to the USB serial driver. This option, chip's called option. These are USB to serial devices. They're modems, they're lots of different things. There's a ton of different ones. And there's no standard for these types of devices, so you have to have a custom device ID for every single one. It's just the way it works. So here's the patch, and here's the description of it. So this is just email.
The description here.
And there's the subject line.
Yeah, using serial option, adding whatever.
Adding that device, and then here's good part about hardest part about writing a kernel change is the description of what's going on.
Really?
Yeah, I mean the code is easy. It's the description explaining it is hard. Right? You don't explain usually what it's doing. You explain why you're doing it. For something as simple as this, it's really easy. So this person says this driver is part of a Cat6 modem. Product ID is shared across multiple modems. It gives a little dump of what it looks like in the device. And And then there's some more information. There's a signed off by line. And signed off by is what we created a long time ago that shows I have the proper authorship of this and ownership, and I gave it to this project under the license by which the project was run. So it's saying I'm licensing under the GPL. And then way down below is probably the one-line patch. This is all just.
So this is all the description.
That's all the
This person giving context on like here's what needs to do
Here's
about
what
the
it
modem, the different
Yes.
specifications or what.
And here's the change. So somebody changed this, remove that line, the red is removed, the green is added.
Yeah.
So somebody added and had to reformat the lines based on the new ones they added. And that's it. So they have a few new device IDs.
And then there's a device ID, and then we see a few hex numbers. Those are like some IDs here.
So for USB, USB devices have a product and a vendor and a product ID. That's how they're
Yeah.
the vendor and then the products. And then there's some sub-device and sub-product IDs.
Got it.
So that's what this is for.
Okay,
So
so
we're just adding support for some, the driver already works for these chips, for this chip, but we just have a new ID because a new vendor came along and they want to put their own vendor ID. So very common.
So it sounds like this change was as simple as it get in terms of the code change, but still the description was very extensive, right?
So very extensive. Part of the description was also just here is a dump of the description of the hardware, just so that we can verify, yeah, that is going to match with this.
Got it.
So just we have tools that create those things, but yeah, it's a lot of work for that change.
Well, but this is like if we talk GitHub language, although I'm not sure.
No,
This would be a PR, right?
This should be in the patch itself, not the PR. So a PR would be, so say you have 10 changes. So a PR would be the patch 0 out of 10.
Got it. Yeah, this is the commit.
This is the commit itself, which is a big problem with why I don't like the GitHub model, is because people don't put the changes in the GitHub, in the Git commit.
No.
Because the Git
You
repo,
don't.
well, there's a problem. When you commit when you're looking at the repo later and you look at the change, you don't see the pull. You can't see the pull request information.
Yeah.
And it's annoying. And that's a big problem, I feel, with the GitHub.
Well, I feel this goes back to, like you built the tool, or Linux built the tool for your use case, and you're using it the way you intend to use it, whereas GitHub built the pull request workflows built on top of this, and it is not part of Git for whatever reason. Maybe GitHub could have made it part of Git, well, no, but it's not, right?
Well, no, so we have pull requests. We create a pull request. In Linux. We email this Git and create a pull request.
Oh, okay.
That was a good command. It makes an email.
Is that part of Git?
Yeah, it makes an email.
Okay.
It says pull from this repo, and here's everything that's in this repo. And when we do a merge of that, that merge commit has all the information.
Okay.
And then so if you look at the next kernel and see when you merge, the latest merges in the USB tree, he sees my little message up saying, here's everything that's going to be in this pull request.
You got it.
And because it is the source, and that's where all the data is, right? And so you can see that when the pull request is not, GitHub could change the model, and then the merge request, it doesn't.
I was about to say that, like, because you did it, they could live this, it's a matter of differences, and, yeah.
That's fine.
Anyway.
But the good thing about this is you can track every single line of code back to who made it, and what they did, and what was the change, what was the reasoning behind it,
Yeah.
which is great.
Okay, so this comes into, this person sends it to this module?
So we sent this to so the owner is Johan. There's a script we have that says take any patch and give me the people who are responsible for this and the guidance. So Johan and me, send it to the USB list and copies of a bunch of other people that I guess they work with and that have changed this driver in the past.
And then the copy is also another tool that, as you said, it kind of looks to who touched this code or who might be, this is all automated.
Yeah, all of it. We do that.
Awesome.
So that was great. We sent it down. This is the one that says 2 copies of it. That's just because they want to do all this. And then they said, oops, I messed up. There's an email from the person instantly after he sent it off.
Oh.
It said, I messed up with the interface. Maybe I'd be a good idea to change this comment. So they go and change the comment. And then they resend it. And you just send a new version. And then
in this case, they send a new patch, or do they just add one more copy? No, you want to have a clean commit, right?
yeah, so here they sent the version 2 patch. And if you see, this is version 2, right? changes in versions from the previous one. And there's a link back to the first one.
Nice.
Very nice. So,
Clean.
so we want to see the changes because I mean I get 1,000.
Yeah.
And when I review patches and stuff, I'll review them and then they're gone. Next one.
Yeah.
But if I want, when you send a next version on, let's see what changed from the previous one, so I want to go back and dig through all that stuff. So they added some information to it. Wonderful. And then